Okay, thanks for joining us for another public lecture at the Center for Machine Intelligence. So I'm James Marshall. I'm the director. I don't think anyone has kind of not seen news about large language models or really doesn't know that large language models are important these days in society and also increasingly in science and technology, of course. And Sheffield also has a long history of metals and metallurgy. And with the Royce Center here at the university, we have a tremendous track record in that. Today, we're going to hear about the combination of these two things. And I'm going to hand over now to introduce our guest speaker to Professor Katerina Christofoidou, who is lead in advanced metals processing at the Royce Institute and professor of metallurgy and
diffusion is a single metallurgy, just to cover all of this. Thanks, James. Welcome, everybody. It's so nice to see so many of you here for the public lecture today. It's a great pleasure to introduce Professor Taylor Sparks, that's coming to us from the University of Utah. Taylor has a CV that will probably be here for an hour if I recounted all of it. But the key things to kind of mention about Taylor, he has a PhD from the University of Harvard in applied physics, was at the University of Santa Barbara before that, and Utah before that. So he's returned to Utah to teach at the University of Utah. A lot of you might have come across him previously through his very, very popular podcast, Materialism. And I think, certainly, having been admissions tutor here, I've seen many people mention Taylor's podcast and what got them into materials in the first place. So for that, we thank you, because we need all the help we can get in materials. But more importantly, Taylor is a massive advocate for materials informatics and the application of AI and machine learning in material science. So I'm going to let him explain what that means in a little bit. But I would like to ask you all to help me thank Taylor for coming and being here with us today. And with that, I'm going to open the floor up. So thank you. And you've got the 26. See.
It's such a pleasure to be here. Thanks for coming. If you've never heard of Utah, it's a beautiful place. This is Salt Lake City, Utah, where my university is nestled right in the corner here. What I like the most about it is I can go from my lab right here to skiing up there. If this is us with the Materials Advantage student chapter doing a ski touring exercise, in about 30 minutes we can be up there, which is phenomenal. And I had the pleasure of telling you about the work happening measured, but I don't do any of it. And so I'd want to make sure that right up front I point out that these are the stars, right? These are the people that make all this stuff possible. And what's cool is, remarkably, when I started this job 12 years ago at Utah, and I said that I wanted to do something with this data plus materials concept, everyone rolled their eyes in my department. Bev, that's not material science. What are you doing? And you look at what we do, look at this. You think this is a CS department. These are the research areas that we do. It's all applied in the materials domain, and there's been this real revolution in using data-driven tools for all domains, including material science. And so I'll try and point out the specific contributions that they get to them. What I want to talk about today about time, and we'll see what I can get through. I'm going to first talk about the traditional ways whereby we go and try and extract data out of literature. I'll talk about how I once considered this an unsolvable grand challenge that maybe by the end of my career would see it happening. This automated generation of materials databases to the reality where it's happening and where the Parker is doing it, which is pretty wild. To get there, I'll talk about what's been state of the art, how it's transformed. I'm going to talk about how really LLMs are changing the way that we fundamentally just interact with literature altogether. And then finally talk about how we're using it for the generation of new materials that were never yet discovered, but could be through these tools. And this work's been sponsored by the NSF, the Steel Founders Society, Thank You Metals, and the Army Research Office. Okay. There are some really great examples of materials databases, and that was because somebody stepped in from the outside and said, here's the format that you have to follow. If you're going to publish a new crystal structure, you have to adhere to the CIF file. This was what year? 1991, not that long ago. In 1991, the IUCR, the organization, basically said the CIF, crystallographic information file, is the file that you will use if you're going to publish in our journals. And since that's where everyone will publish, everybody shifted. But that did not happen in the rest of the material science domain. There is no materials information file that college journals accept. And so it's been the Wild West. People just publish all sorts of stuff. And the tools that have been built to try and pull that data out of the literature have been ineffective. Honestly, it surprises me that they're not that old. 2010, basically. 2010 is when we started doing this. And some of these like well-known tools like Chem Data Extractor are not that old. Comes from England, actually, that one. And these tools, early days, they relied on what we call semantic search. Essentially, what you're doing is if you control the effect of the document, you're saying, look for key names of chemicals, very specific names of synthesis procedures, and you're trying to use a rules-based approach, which sort of assumes that you know the grammar that the authors were using when they wrote this paper. But the problem is that authors are complicated, or humans come up with all sorts of crazy ways to write about how we make and measure and test materials. And so while it would work okay for sort of patent literature, which has a little more structure, these did not work particularly well for common literature. So enter the era of natural language processing, pre-LLMs, right? These were the small language models. And these got a little bit better. And this is about when I first started paying attention to it. I remember being at this meeting in 2018 or 19, this is 2017. And I saw this paper presented by Elsewhere. It was a pretty impactful one in our field. I think a lot of people sort of took note when it came out. And they used these sort of small language models to grab data from the literature, and they presented all these interesting talks. And I remember sitting in the meeting at the MRC meeting and presenting like, oh, God bless them. I'm glad someone's out there trying to do this, but this is just not ever going to work, is it? And I sort of was, again, relegated to an unsolved problem. Well, those here in this room, the Center for Machine Intelligence, you know what happened here in 2018, right? We had the birth of the transformer architecture, right? And things, boy, did they change. All of a sudden, you saw Cybert and ManScibert and ChemBert. These language models are now trained on very specific corpus of domain text, start to do a lot better at this task. It still wasn't enough to convince me that this grand challenge was solved, but that changed in December of 2022. December of 2022, this preprint comes out. It later got published in 24 in NatureCom. But I saw this example where they took a GPT-3 and they were able to take and do a bunch of hand labeling, generated with a bunch of unstructured data coming in, abstracts, and structured data with a lot of human effort. They get about 100 examples. And then they have a sort of partially tuned model, and they try and turn it loose, and it makes lots of mistakes, but they sort of babysit it. And as it makes mistakes, they correct it. Oh, no, that wasn't actually a solid solution. It was something else, right? And after they got around 500 examples, now you've got a fine-tuned version of just a GPT-3 that can do a pretty great job of taking unstructured information, making it structured. This is one that changed my mind. Now, that said, this had some serious limitations. The reason that they only looked at abstracts was the token size limitation, which existed back then. You couldn't feed it all the way. For a paper that's 30 pages long, it didn't know what to do with. You run into errors there. And there's this pretty painful labeling section, and you know that probably for it to be good for your field, you have to do your own fine-tuning for your specific field, which is a bit disappointing. That said, we saw this approach pop up in literature all over the place. Here's one done for, what's this for? Perovskites. And it starts showing up all over the place. The real next innovation, though, happened with ChatGPT, right? GPT-3 had been around for a while before ChatGPT showed up. But the one that caught all of our attention was ChatGPT. And this was because it relied on, again, people from likely know, but RLHF, reinforcement learning with human feedback. You can achieve alignment. You can make the model behave a little differently than the pre-trained weights would suggest for it to train. And basically what they have it do is they have the model create outputs for a given prompt, like extract the data from this, right? And that's how they did ChatGPT, right? But then when it generates outputs, they have a human score these things. So if you had 4 outputs, you could rank them. Well, that was your worst response. This was our best response. And this really made it a lot better, and it made it much more generalizable to the task of pulling data out of material science literature. And now you see this RLHF sort of approach all over the place. Here's one for off synthesis where they're able to grab this and very effectively pull data out of it. Here's another one. In this case, they asked it, with and without basically text pre-processing and token prompt engineering. And the point is that this was sort of the state of the art when we looked at this, and it was pretty effective. So having given you an idea of the challenge and the promise that's come along in just recent years of, holy smokes, we really could maybe start to assemble materials databases. Now, how do we make it actually happen? Well, in January 2023, a month after we saw that breakthrough paper, we decided we'd jump on board. We said, well, let's give this a try. And we tried to do something a bit different than they did in the original. We didn't look at the abstract where there's some materials data. We went right to the meat of the paper, in the experimental section, right? In the experimental section where they describe what on earth they're doing is really rich with information you'd like to extract for the metadata if you're trying to figure out how to make things. So that was one thing. We wanted to eventually look at the entire paper, but we started with the experimental methods section. And another thing that we wanted to avoid was this 500 examples of human label, which is a real pain in and out. Honestly, I'd like to avoid using OpenAI because I went through like $5,000 in API fees in the first weekend we tried to do this. So we wanted open models. We wanted to get past the token size limitation. I didn't want to hand label. We had pretty tall order for effective what we wanted to achieve. How we tried to do this was taking advantage of work that's already been done. There exists something called the polyfile, materials, MTDS with sample and materials Project Data, I never recall what it stands for. Basically, they take retired engineers and they have them read scientific literature and pull the data out by hand. And if you pay a lot of money, then you need access to this. What's nice about it is that's tied to a DOI. So every paper has a specific identifier. You can use that identifier where some expert has created labeled JSON format data. You can take that same DOI, you can pull the original paper, and we thought, well, we've got a bunch of labeled data, don't we? This doesn't fix the token size limitation. So we need to reduce the token size nowadays, Now with RAG systems, they're able to get around that. But back then we didn't know what to do. So we knew that we had to do something to reduce the token size so that we could look at full papers and not just tiny sections at a time. And here's the process where I did that. The first thing we realized is that we needed some tools to actually look through PDFs. And there's been some amazing tools from surprising places. That comes from Meta, right? Facebook company, right? They released this NuGet, Neurological Understanding of Academic Documents. It's a phenomenal tool to take PDF and create a version of the PDF into what's called Markdown language. Why we like that is because it does a great job with superscripts, subscripts. It's very effective. It's actually really good at tables. This was a long-standing problem in pulling data out of tables, is you have to make sure that things line up. Just human can do no problem. You look at the table, it's easy to sort of follow the line over, but previous computer vision tools for this were not very good at this at all. But here's the example. The table on the top there is one that comes from an actual IA. Let's imagine it's an image-only IA, right? So you can't convert that markdown with other tools. But this thing converts markdown. Here's the tech version of that table. And then when you put it to overlay for something and reconstruct it, you see very good matching. It will occasionally make some mistakes, but it's quite good. So now that we've got the right kind of tools for this, we started to scratch our heads and say, well, what does the material science text specifically look like? So we did a preliminary study with Wave, Hassan, and Sterling, where we just said, material science is a very, very broad field. There's glass experts, there's steel, there's inorganic, there's polymers. It's very, very broad. So we intentionally looked at a lot of different text in literature to figure out what it looks like. Starting with the text itself, we said, what type of information do you find when you look at academic papers in the material science domain? Well, you find named entities, like the names of compounds or formulas. You find processing conditions. It was sintered, it was annealed, it was cold forged, it was cast, right? You find characterization techniques. We did X-ray diffraction. We put it in a microscope. We did whatever, right? And then properties Gipper pulled it. And these four things all show up in the text office. So you're scribing in your paper. But when you look at tables have different information. They're very rich in some things, like named entities. Some characterization typically heavy on properties. But they don't describe as much the processing conditions. And figures are very different in their own way. Figures sometimes have named entities. You can find the legend of these things accurately. They typically have the most properties, like the full details, right? The raw details. Every time you data one of the spectra, as you technically, in some cases, see in these things. But the refined information from these, like what phase is here? Well, that's trickier to turn from this. It's showing you peaks, like where the reflections are at, and every tiny bit of data, but they don't have all the same information. In fact, when we sort of looked at the aggregate, looking at a bunch of different papers, here's what we found. Again, this is a little bit anecdotal. It wasn't like it to every paper, but it's a pretty broad overview, I think, of material science. When you look at text, you find awful things, but you don't find all the properties. If you look at tables, you find strength in some areas. It's look figure. That's really where the properties are at. The problem is that the tools for extracting data from figures are not nearly as robust for text. Large language models are slowly being replaced by multimodal models, which are variations of language models, but they're not there yet. That said, I was telling this not too recently and not too long ago, and somebody told me, actually, these language models are getting pretty good at pulling data out of figures. So let me show you some of the stuff that's relatively hot off the press here. Take this figure. This is like an XPS curve, something like you'd see in a material science paper, where it's showing you a binding energy as a function on, it counts that you would see as you XPS or something. And when I just asked a couple different multimodal models, ChatGPT, doing it manually and using complexity, which since done it a bunch of others, it's encouraging. It's not exactly right. In fact, if you're an XPS expert, you'd be like, oh gosh, 2 electron volts off. That's a world off. And the fact that it's able to get it even close, to me, is pretty remarkable. I was pretty excited about this. No, this was one of the better examples. Here's another one. It's a bit messy because in this case, we've got something done as function, 3 different frequencies, 1, 10, and 100 kilohertz. And so I should have done one at a time. My takeaway from this, since you have time to really interpret this plot, is that it's okay. It's making some mistakes, but it's getting the general trends. Again, kind of promising. But look at this one. Very simple plot, I thought. The machine learning does not know what to do with this dotted line. A human knows what that means. there needs to be some additional training to these models for them to capture some of that. It's doing actually not a great job with those sort of things. In other areas, it's quite good. Take schematics. In a lot of material science literature, we represent things as steps. You do 10 different steps before you get your final product. And it does a great job of understanding images just like human, honestly better than human in many cases, I think. Does a pretty fantastic job. So my takeaway for the current state of the art using language models for getting data out of the literature is fairly positive. We can go from PDF to markdown text in many cases. Even when we can't, we're starting to get directly from the figures of computer vision, which is exciting. What about the token size limitation? Well, some things we were working on that was with executive summarization. So given this big long document, I ask a language model chunk by chunk to go through and say, just pull out the necessary bits, such that a second language model pass through could just work on the extraction. That's varying degrees of performance, right? Summarization can do kind of okay. You could ask that to happen with no training, to say, summarize it for me, right? Or you could do one shot where you give it an example. Summarize it. Here's what I'm looking for. Had this been the input, this is the output that I expected, right? We see varying degrees of performance here. Here's one. Here's a block of text, right? 157 tokens. And then I say the text is just, the prompt is just summarize text. So I don't tell it exactly what to do. I just summarize it. And it's able to take it from down to a third of the tokens, which is pretty slick. But it's left off a bunch of the important information in the process. So we try it again. This time, let's give it better instructions. I say summarize the text. Make sure to concentrate and provide any performance metrics, measurement results, related numerical data while keeping it concise. You see 157 down to 50, and it actually keeps all the data corrected this time. I feel pretty good about that. And then we try it the exact same block of text twice, and you get once it might work and once it might completely hallucinate. Just a bit frustrating. That said, it does an okay job. Text is doing weird things on the screen. It does an okay job of finding categories that humans wouldn't struggle with finding the right structure for. So it actually works pretty good as a first pass if human is involved in the loop, but not amazing. So my takeaway on this one is fine-tune models. We're going to need them for material science data extraction. These generalized LLMs, ChatGPT approaches, they're probably not good enough yet for this process, but they're getting pretty close. And in order to fine-tune, we still need gold standard annotated data sets, hence where the polling file came in. Here's an example of polling file. I was really excited about this. Here's some entry from some paper. And then I got to looking close at here, how we were a bit disappointed because what they did is they're reporting basically one measurement at one temperature. But the text is full of lots of measurements. And whoever the expert is that's annotating these things is giving you a flavor for the properties. They're not capturing every single data point. This is going to cause a problem if you give it the text, which has all of the data there, and how is it going to know which data point the human expect? It's challenging. It's not getting all the data we want, and it's going to bias it in a way that we don't understand fully. So that was unfortunate. And to get around it, we turned towards structured prompts. Structured prompt is basically you're giving it a clue on what you're looking for during the text extraction process. And we used Gemini Pro for this because it was free at the time, and it was doing a pretty good job. Basically, we took blocks of material science text, and here's our prompt set. You're a lean, materials data extracting machine. We want you to get the data out. Had this been the input, this is what we expect as an output. What I liked about this is that you could do, a few shots, you do 1, 5, 10, however many examples you wanted. And with only 5 examples, we found that this was really, really high performing. Some examples, right? Summarize it. Had this been the full block of text, the label you might have provided is something like this. Go ahead and summarize it down with something smaller. Or maybe it's organizing it into a JSON structured data format. Given this block of whatever, turn it into that. We tested this on a bunch of papers, and 10 of them. And what we did is we only did 5 examples in our structured prompt, which is way easier to do 5 compared, way easier to do, right? And then we compared the output of 5 different outputs by hand to see what the stochastic nature was, because we know it's going to have a little variability. We compared those with hand label responses, and what do we find? Well, at first, we were using things like the Rouge score. If you're not familiar with LLMs, the Rouge score space that says when there's an output, what is the score versus what it's supposed to be? What are the outputs that it got versus what it's supposed to see? So let's say the output was supposed to be the fox jumps, but what the LLM spat out was the hello cat dog fox jumps. Well, the 3 words you were looking for were there, but 4 words that you weren't looking for were there. So the precision actually is suffering. You've got a 3 out of 7 precision, but the recall is perfect. The recall says that the 3 words that I was supposed to find, they're all there. And so obviously you can combine these using Rouge scores and end up with some net composite score. In this case, maybe 60% is your F1 score. Now, what most people do in the LLM world is they say Rouge isn't perfect because it doesn't care about the word order. fox jumps dog is not saying as dog jumps fox. Word order matters. In other words, word context matters. And it also messes with things like synonyms. For example, the phrase, the weather's cold today and it's freezing today, kind of has the same meaning, doesn't it? So those should be scored as being similar, and Rouge score would not do that. So transformers are a great tool for remedying this, both word order and synonyms. But is that the right metric for materials data extraction? At first I was like, oh great, we'll just use this because look how great for you. We get like 90% scores, we lost or whatever. In fact, here's the actual scores. Like look how good we do with fur. It's awesome, 92%. It's terrible if the Rouge scores. But I've come around to think that I think Rouge is what we're looking for with data extraction, isn't it? If I'm going to be extracting data from the literature, I don't want to get kind of the right magnetic susceptibility. I want the actual number going. So I think there's some work to be done still. This isn't yet a solved problem, but I'm certainly convinced that we've gone from grand challenge, who knows, in my lifetime to, yeah, this is happening now. In fact, one of the breakthroughs, I don't have slides for today, but we certainly will press that. If you just break the process up and you do property by property, you see a huge improvement in performance. Instead of trying to catch it all at once, if you're willing to spend the cycles to a property by property, it does far better. When a sort of agentic approach, where you're saying, you specific agent, I'm looking to this, you get much more fine tuning there. Anyways, and you can skip this 500 samples process. You can do it just 5. So we published this in INLM, Integrating Materials and Manufacturing Innovation, and I'm pretty happy about it. So that said, that is the current status of pulling data out of literature. Again, I think it's here. I think that it is now here. For the longest time, I griped that material science, boy, we could do a lot better in materials informatics, machine learning materials, if only we had data and if only we had some agency to enforce a materials information file format. And how do we need that anymore? I think that we can get right out of literature with tools that I never dreamed could exist. So it's a great time. Let's now talk about how we can interact with literature in different ways, not just pulling data out. What about pulling knowledge and information and interacting with the data in different ways? This was from the Steel Founders Society. They basically, it's a large consortium of U.S. steel founders in the United States. They've got 60 or so foundries, as much as we still make steel in the United States. And they have gigabytes and gigabytes of internal notes and reports on how to make different things. And in the past, their members would pay good money to be part of this consortium just for the privilege of control Fing through documents to try and find how to make 4340. If it's 5 centimeters thick, how do you temper it, right? And they hoped and prayed they could find something that's non-IQ legal about it. So they paid us to figure out how to interact with that literature in a different way. And this was inspired by my own search, right? When I was 12, 13 years ago, a postdoc, we were trying to pull information from the USGS Mineral Commodity Survey. As you may have heard of that. The United States Geological Survey essentially goes around the world and estimates who has what minerals, are they making them, who's making them, what are they using them for. These are really cool documents. If you get a minute, like them very easy. For every major commodity, you can find it. It'll tell you country by country, who's making it. They do these every year. It's a massive effort. It's a massive effort. They put them into PDFs. They're the worst. You have to go one by one through these things and try and make sense. It's just a pain in the butt. We did ones in 2012 on the 2010 data, and it was a huge amount of work. Huge amount of work to digitize this and put it in spreadsheets where machine learning experts could do something with it. And then 10 years later, it's already out of date. I was already going back and doing it year by year. There's got to be a better way. There is a better way, right? And nowadays, language models evolved dramatically since even just a couple of years ago. Now we have RAG systems. Just quick show hands, familiar with the term RAG. Who's familiar with these systems? Maybe a third of us. So RAG stands for Retrieval Augmented Generation. It's a type of LLM where you're sort of cheating. If you remember early days of ChatGPT, you asked it, it was trained in 2021, if you recall. And very next year, if you asked who won the Super Bowl 2022, it would not give you the correct answer. It would just make something up because it'd only been trained in 2021. And it would tell you, look at it, hey, I was only trained in 2021, so I might be full of crap, right? And it was. The way that they fixed that, rather than spending another 10s or 20, we don't actually know how much they spent. We know they spent about 10,000 core, like GPU core, so it was a big effort. Many millions of dollars to train it. You don't want to retrain it every year. And you don't need to. Instead, what you can do is you can build a RAG system. And that text got really messed up. Where essentially what you're building is a pipeline that looks a bit like this. You start out with document loaded. The answer to your question exists in some document. Let's say like the wiki page for Super Oliner, right? You take that and you split that document up into chunks that your LLM can ingest. Then you store those into a vector storage system. What's missing here is some sort of step to assign a meaning to each block of text. One at a second. And then when you actually get a query, like who won the Super Bowl, the task of the RAG system is to pick the right chunk of document that you think contains the answer, and then answer the question using that chunk. Now, there's some steps that aren't shown here. For example, when you get your original block of documents, right, you break them into chunks, you need to do what's called an embedding. An embedding is simply turning this block of text into a mathematical vector. We do that such that when you ask a question, that text turns into a mathematical vector, which is just like a vector pointing in hyperspace somewhere, right? So this is the question. And then it scans through all the information that you have available to broken into chunks, which has a bunch of crazy directions too. And you pick the one that's most aligned with it. And then you send that to the language model and you say, the user wants to know the answer to this question. By the way, I think the answer is down in one of these couple chunks. And you send it a few chunks, right? Not so complicated, but very, very effective. So using this type of approach, we were able to build a RAG system to the USGS, which took all of the effort that I put into some of these early papers and made it completely redundant. It's amazing. You go to right now to mineral-ai.net, and you can just ask the chatbot. You can say like, what was the HHI for niobium in 2017? And it will tell you exactly what that was with a very simple sort of RAG agentic system. If you haven't built these things before, this might sound intimidating, like there are steps shown here. It's not that complicated. In fact, my student made it dead easy. He built something called RAG Skeleton. Why didn't name it RAG Skeletos? And this opportunity for sure. But it makes it really easy. You can download this from Python with minimal tools. You can upload your documents. It'll parse it. It'll embed it. It'll build the matching thing. All very simple. It's modular. It works with modern libraries. It's just great. It makes it very easy. So let's show you what this looks like. I can't show you for the steel example because it's all privileged information. So instead, I'll show you a dummy example with a couple papers. Here's a couple Farovsky papers that we just pulled out of open access articles. And here's the system in operation. So let's start here. So here's running up currently. You could build a movie if you want. It'd be very simple. Skyjo. Maybe. Oh. Maybe. Even if I go. Ooh, we just missed the cap. Duplicate. Okay, ready here. You might have to take my word for it. Get some pitches. One more try yours. Can you just play this? So, it's broken. That's no word for it. Anyways, it's made it dead easy. Easier than embedding in your PowerPoint for sure. That's funny. What I've done there. So check that out. It's on GitHub. Again, we made it very easy. You can pip install this thing and be off to the races. In fact, in my last workshop, I did this during my talk. I had my student request a couple PDFs from the audience. And by the time I finished my talk, there's no fine tuning involved here, right? So by the time my talk was over, he was able to have the questions from the audience prompted to the tool and get expert responses right on the spot. Very cool, I think. So what I like about this is that first off, it's a lot easier than scraping data out of these tables and trying to get the understanding. And you can leverage the knowledge and understanding of these large language models in a way that's just effortless. Why does this matter? How many papers are published each year in your fields? A lot. In material science, it's exponential growth, the number of papers. I haven't done it in the last couple of years, but in 2020, I did it. And in all the areas that I care about, batteries, nuclear, whatever, there's on the order of 10 to the 4th papers per year. That's not cumulative. That's per year being published. And how many papers do you read every year, Kathy? Like, how many do I get asked to review or around that number? Right? I mean, it's wild. And so we're either discarding that information or we make you're only reading from the top journals, which is silly because who says what's top? And does that mean we're just tossing out information? No, like we've gone beyond what individual humans can do. 100, 200 years ago, you could have these professional societies where a couple dozen papers were published and everyone could read them. And that's not the world we live in anymore. And if we want to deal with this deluge of digital information, we need tools like this to help us understand it and interact with it in different ways. And I, for one, have just talked about RAG systems for doing that. Okay, let's do our last one, which is generation of new materials. So this is really exciting. All right. I started on this during COVID. When all of our labs shut down, I had a couple of students who wanted to do this idea of honestly fixing a criticism that had been a long-standing criticism when I would go around. I've been doing materials plus data for 15 years, almost 13 years. And when I would go around and say that we used such and such a machine learning model to predict properties, and then we screened for all those materials and found some breaking material or something, we found some awesome materials that nobody knew had that property. But when I would call it discovery, I'd always get some gruff in the back say, that's not discovery. You just identified a material that already existed as having the properties you cared about. That's not discovery, is it? It's high throughput screening and identification, which I would argue is still super valuable, but it's not discovery, is it? And that's a little disappointing. True discovery means that you're not just pouring into the top of your model all known materials. You're opening up new potential materials. And so we spent a lot of time developing tools for this for about 5 years, right? Till about 2024. This paper was published in 2024. We had a bunch of this. And we used the Gen AI tools that have become very powerful in this field. These like conditional GANs or diffusion models. In goes random noise, out comes a new material. And there's a lot that goes behind the scenes of that. But we were excited about it, and this works pretty well. And we're not the only ones doing this. Big companies are doing this. Maybe you've seen some of these papers. This one is, let's see, this one is Microsoft. This one is DeepMind, so Google. Meta has one as well. The big tech companies are doing materials research, generating new potential crystal structures. And some of the languages over the top. Well, these are both Microsoft, excuse me, but all the big companies are doing it. That said, most of the generation up until very recently has been unconditioned generation, just random noise. And it's just randomly going to create structures that look kind of like the ones that it was trained on when it learned. That's not conditioned generation. Conditioned generation is much more interesting. In conditioned generation, you're saying, give me a certain structure, but it matches this condition, right? Create a perovskite material with a very specific band gap, for example, and maybe we can create that very specific thing. There's this great article that came out by Aaron Walsh at Down Imperial, where he pointed out the just mega number of papers showing up in this area. Look at this, like, is this 2 dozen or something papers? Most of them are using variations of the tools like the ones we built. Conditional GANs, variational autoencoders, diffusion models. But there's a couple that showed up that really caught my attention. This one right here, this autoregressive transformer by Tunis. This is done down at University of Reading by Ricardo Prespo's group. And I was actually there. I was here in this sabbatical a couple years ago on my, in the UK for my sabbatical in 2022. And I met Louise. He's actually in Canada, so I met him over a Zoom call. And he told me what he was trying to do. I said, wait, what are you doing? You're using a language model to generate structures? And I remember telling him this is a terrible idea. This wasn't going to work. And it wasn't even a large language model. It was just an autoregressor. Basically what they did, in this paper, you can read about it. It's become very important paper. They called it Crystal LLM, right? And essentially, the CIF card that I pointed out the very first slide of my talk today, this format that we all follow when we're doing structures, it's just text. If you look at it, you have to kind of be a domain expert to know what you're looking at, but it's just describing what's the shape and size of the unit cell, where are the atoms located at, and it's all just in text. So the crazy thing I thought that they did is they basically said, if we want to generate new structures, what if you just get at the first line of that text, like I want you to make potassium bromide structure, and then you just let the autoregressive transformer rip. So it's not even a large language model. It's just a word predictor, predict the next words in sequence. I did not think this was going to work. And to my surprise, I had to eat crow because it was pretty well. Again, this text is all over this. I apologize. But what you're seeing, forgive them for the mess here. In this table, they're showing you benchmark performance against some of the very best crystal graph, diffusion models, like the biggest, burliest things that Microsoft and company and myself were doing. It's on par with those, and it's not even a good language model, which is shocking that it's getting even close, let alone being competitive in some ways. So then Meta comes along. Meta has much more resources than University of Reading, and they really throw the kitchen sink at. They use a proper LLM. They're using Llama 2, 70 billion. That's a lot of parameters. They actually do fine tuning on this. So they spent some serious compute fine tuning their large language model on this. But they also did some strange things. For one thing, these crystallographic information files have a lot of text. It describes the shape and the size of the unit cell in the context of all this stuff, like it mated, where the atoms are. Surprisingly, they pulled all that information out, just created like a mathematical matrix of that information. And that's what they fed the language model, which still, I asked the guy on my he was actually on our podcast, my pod, you did that. The whole point of language models is words in context of other words. Why did you pull out the other words? They didn't have a good answer, but they did it anyways. And this gets even better. We saw this, and they, by the way, they started to do now. It's proper LLM, and they conditioned it. They could say, here's a description, here's the formula, here's the space group, making some property, and it's able to do condition generation pretty well. If you get really specific, starts with vol in some areas, the overall, you get getting it right half the time. That's pretty amazing that it can generate a structure and half the time get something reasonable. That's what from a language model. Now, there's some challenges they did. If you were going to try and copy yourself, you need a lot more computers than anybody here probably has. They got some serious resources. So when we wanted to do this, I just dropped 30 grand on a new GPU thing, and it has not even anywhere close to train. I need 60 grand just to fine tune Llama 70 billion, and I didn't have that. So I certainly don't want to dedicate it to that only. So what are you going to do? Well, there's a lot of models out there. And if you see like the size of the model, let's see, this is performance. This is as the year they came out. And then the last number tells you how many tunable parameters you got. So Llama 3.1 70 billion is not like wildly better than their 8 billion model parameter. Like you look at the performance, 69 to 84, still pretty good. 8 billion model parameter, and it's a lot less memory. Plus, we don't even have to fully fine tune that thing. You can do what's called Q-low rate adapters to fine tune it, which is essentially a cheater way to fine tune it. Instead of messing with the weights in the neural network that cost you a lot of money to tune, what you use to keep these frozen, and you fine tune something, other parameters that have lower dimensionality, which have the same size. And these are, then when you put these two things together, basically, you get a facsimile of fine tuning at a much less memory cost. So this works all right. Here's what we built. We call CrysText. Show you it in operation in just a moment. Here's the inputs, right? The input is basically, the prompt is make a structure, right? We give it a little more words than that, but it's basically like make a structure, pay attention to the instruction and the input. So a typical instruction might be like generate a sieve for the given materials description. And then here's the description, the input B. The composition is whatever that composition is. It has a space group at 225. So now we're going to do conditioned generation, where it's going to force it to make a structure that has this chemistry and that symmetry, right? Or you don't have to use symmetry. You could also do like some description of the material's properties. The data that we trained from to do this fine tuning was the materials project data set called the NP20, because it considered any structure with up to 20 unique atoms in the unit cell, which is just a way to make it a little bit easier. These are more simple than big dollar ones. Still pretty good structures though. Here's it in action. See if this video works. I'll be so sad about that then. Oh, what a bummer. I think it's because I'm not connected to the internet, baby. Let me just double check if I hop on Edge Realm. I'm on Edge Realm. It's a little bummer. I don't know what's going on. Well, I apologize. Take my word for it again. It works great. You can find the paper on Chem Archive. We've got it on GitHub. You can see it. That was very disappointing. Essentially, you can just give it any description you want. And in real time, if that was fast as ChatGPT, you'll see it start cranking out words one after another that form this sieve file fairly quick, much faster than our diffusion models that we were doing in the past. And how effective? Quite effective. You know, my student Trupti, she's phenomenal. She's like an overachiever. She created this plot theme, which shows you when you generate a specific structure, assuming you knew what the structure was supposed to be, but you never let it see that during training, then you ask the model to make that structure. How often does it match? And what does it even mean to match? Well, there's tools for determining match. PanatGen is a great Python package that tells you, basically you can set tolerances, like if the angle is within 0.1 degree or something, or if the atom position is within like half an angstrom or something. I don't know what the values actually are, but presumably there's things that we just use what everyone else is using in this field, like the accepted tolerance values. Then you can see how many guesses does it take for it to match the structure. And she was disappointed that after one guess, it was getting it right about 60% of the time. I was delighted. I was just tickled pink it could do that. You mean every other time it guesses it right? That's phenomenal. And if you give it up to 20 guesses, it's like 3 out of 4 times it will get it right, which is amazing that a language model, there's something about the way that we encode how humans talk with words is able to, in that barely fine-tuned, with Q-low rank adapting, like ghetto tuning basically, we can get it to generate structures where there's a lot of complexity and a lot of nuance. And even if you do one shot, you're getting it right half the time, is just stunning. It's absolutely stunning to me. We just did an episode of our podcast with Microsoft, who has not yet embraced large language models. And I asked him if he was scared. Because Meta is doing a great job of this. And he said, well, we're going to start. I mean, they have enough resources, they can just do all the above, and they are now. But pretty remarkable. It does make some mistakes, and it is a bit class imbalanced. It's very class imbalanced. Not all symmetry, that can exist, the ways that atoms can organize themselves, they're not all equally possible. There's technically 230 unique symmetries in nature, right? And like 10 of those are common, and the others are not all that common. And so if you take a common one, like 225 in the top left up there, that neodymium, silver, and mercury compound, that's an example of a very common structure. And if you look at the error, right, our RMSE distance, think of that as like the error of how far off are the values. They're not far off at all. It's very good at getting those ones. But if you look at these other ones, which are much less common structures, symmetries, the errors are much larger. Still very good, but much larger. So this is something where there's systematic error here. You could improve this with oversampling. You can improve this circuit with more data. There's more work to be done. But my takeaway is that it's pretty dang good. Like, this is like certainly good enough to start doing stuff with. It will get some things wrong. One of the main things where it'll tell you that it's a valid structure in that it didn't find anything wrong with it, but a subject matter expert level there's a problem, is usually when it swaps atom positions. It'll put the red where it's supposed to go where the red's supposed to. It's swapping positions. So it's technically a valid structure, but a crystallographer will say, yeah, but no, this is not the right structure. That will happen in some cases. All of these are examples of that. And it'll do some other weird things. It is a language model. It will still have, some crazy hallucination. Like, here's the actual structure for this thing, and here's one that got generated. You'll notice right here, the atomic positions, the X, Y, and Z coordinates. I don't do it through in gdyn.com. It does. It was very popular, apparently enough to get in my SIP card, though. That'll happen sometimes, right? These aren't common, but they happen. There are some errors where you create invalid structures. Sometimes they'll do things that are more subtle. Like this one, the crystal structure was, this was tricky. So again, it's saying that lithium is occupying the position at half in the geometry of the unisol, so right in the middle. But it's also saying that silver is occupying half, which is not common in the world of crystallography. Multiple atoms can share a site, but not at 100% occupancy each, right? It could be 50-50, you say 25, it can't be 100-100. So it'll do some, things that a crystallographer would say, that's violating physics. And so what we haven't yet figured out how to do with these language models is to do constraints based off of knowledge, right? We have a good feeling of what things are allowed and not allowed. And in the world of graph neural networks, we have better tools for this. There are equivariant neural networks that can force symmetry constraints as you create materials. We don't have those. Well, no one's demonstrated those for language models. They might exist. Maybe I see us see an opportunity here, but that's something that could definitely be done to make this work better. Another thing it'll do wrong is sometimes it'll tell you it obeyed the formula, but when you do the math on where the atoms are, it didn't quite add up to the same number. Like this one had 4 molybdenum atoms instead of 3, and so it technically did it wrong. But that said, it's pretty darn good. What you're seeing here is 7 different comparisons of histograms. In each one of these things, you're comparing different aspects of the structure, right? Doesn't matter what they are. The generated structures are shown in pink. The training data is shown in gray, and these look like decent overlaps. Whether it's generating the size of the ABC lattice parameters or the space group number, it's matching pretty well is the takeaway here. The fact that it's doing as well as it is compared to, again, the state-of-the-art approaches, which we've seen in other areas, is shocking to me. Pretty wild. And it's doing a good job of exploring the breadth of the late space over which it was trained. It's not just, doing mode collapse, pulling from the same area over and over. Again, the gray points are your training data. It's pulling from condeveloped. It'd be better if I showed this as kernel density, showing you where, because it just all sort of covered, but they're not equally distributed. So I need to replot this showing you density, but it's doing a pretty good job. To the point where now these language models can genuinely turn out new materials, which is pretty exciting. These are new materials. These are not, materials that existed and now we just identified what properties they're good for. These are genuinely new materials, which is a really exciting time to be a metallurgist, a magnetism person, a polymer person. There's just, it's wide open what we can do now. And when you compare that with the way that Sheffield should know, right? Harry Burley, I think, our discoverer of stainless steel right here in Sheffield, the way that he discovered that was not with tools like this. The guy was building cannons and bits of metal that were going in the bin weren't rusting, and he noticed it just out of dumb luck. He had his eye, I guess, on it. He noticed it, and all of a sudden he realized, well, that steel's not staining, and thus we have stainless steel, right? That was happenstance. That was serendipity. And we had a tool to overcome serendipity. If you believe it or not, like the vast majority of the interesting materials around us, huge numbers of them were sort of accidental discoveries. And for the first time, we got a way to do conditioned generation of new materials. We can take luck out of the equation and we can start finding materials that have targeted properties, which is pretty damn exciting. So some important things to end on, just to seed discussion. I'm almost time. One question, which I think still remains, has been doing some work on, is what do we mean by new, right? Oh, by the way, this is published, so take a look at it. But how about this? What do we mean by new? Because I'm sure you've seen things like this. A generative model, whether it's diffusion or whatever else, can read in something, right? This is what it's trained with, this is fine tuning. And when you ask it to generate versions, it'll riff on that. But how unique are these? It's kind of an interesting thought, right? But in other words, these structures that I showed you, are these just like variations of known materials? Because if so, that's not quite as exciting as a new funky way to organize matter, right? And so to answer that question, like, what do we mean by new? I would argue that we need new tools to measure newness, novelty. And I think you can do so across different axes. For example, you can do it based off of chemistry. Is it a funky new chemistry? We have a paper on that. We published it Digital Discovery a couple of years ago. It uses the element movers distance, which is the Berthon-Rubens algorithm applied to the composition-based feature vector way of representing materials. I think it's a clever approach to encode chemical novelty. And it's a preprint right now, it should be out soon, did the same thing but for structure. So in other words, if a structure is a close relative, like a tilted perovskite as opposed to like a cubic perovskite, it scores low on the novelty here. But if something of a wild new arrangement of atoms, it's going to score very novel. I don't know if industry cares about this, but academics sure as heck do. We want to find something that is unusual. It's breaking the rules. We don't know why it has the properties it has. And for the first time, I think this gives us a way of assessing that is genuinely a different thing than we've seen before. All right, I'll wrap up on this. It'll be my second to last slide. I'm the editor at a journal, the editor-in-chief at Integrating Materials, Manufacturing Innovation. Everything that I've talked about is in the scope of what we published there. If you work on digital material science in any aspect, whether that's CalFat or whether that's ICME, whether that's machine learning, I will love to see your paper. I have some great things to say about this journal. First up, it's free for all TMS members. It's a professional society journal. If you hate the greedy, academic publishers, you ought to think a little more kindly about the professional society journals because they're run by us being me. We have a decent impact factor, published data sets, tools, research reviews. And something I'm really excited about is for every article, I offer a custom editor's video summary. What I do, I make a brief little YouTube video of your paper, describe what it is to people. It ends up on YouTube where I've got a pretty big channel. And what I'm seeing so far is that this is leading to more people reading and citing your papers, which is slick. And last thing I'll show you is that YouTube channel. I put a lot of teaching resources online, so like and subscribe. Love that. For example, materials of derivatives, everything that I talked about today, if you're hearing it for the first time, the context of materials, and you wouldn't know where to begin, I can tell you where to begin. So this is a great place. We talk about the basic tools, how to get started. It's all free. It is the exact same course I teach at University of Utah, but we do it for free, at least until they stop me, right? And so we have that. And we also have a podcast, which I'm really excited to come out. So with that, I appreciate your attention. I'll take any questions you have.